Okay, guys, we're back to it. And where we left off was the structure of Lewis dot structures and a couple of structures of these molecules that we kept drawing over and over. And I showed you electron potential maps, which was basically a diagram that showed you red negative areas and blue positive areas that's generated by a computer. And I told you there's other ways to represent structures as well. So what you're seeing on the screen right now is just more versions of the way that we represent structures, especially in organic chemistry. So what you're seeing here to the left-hand side are things that you typically will draw throughout this semester. And these are what I would call typical stick bond structures. So as you can tell, this carbon in the center has a line that points up and a line that points to the left. But if you look closely, you'll see that this line here in front is a shaded wedge. And then here in the back, you see that that is a dashed wedge. The reason that they're doing that is to give you an idea of 3D. This molecule is in 3D. It takes up space. I keep saying it over and over. I know, but I need to get you to understand that this is the way structures are. The quicker you can accept that, the easier time that you're going to have in organic. So this solid wedge, that is typically a representation of pointing toward you. So this bond is actually facing your face as you look at it. This dashed wedge that's here in the back, the dashed wedge means that it points away from you. So it's going away from you because it doesn't like you very much and it wants to go in the opposite direction. Again, it gives you an idea of 3 dimensions. Well, this is what we draw most of the time on a sheet of paper. We can do this very easily. It takes a little bit of effort or a little bit used to getting to, but you'll eventually get there. Well, to the right-hand side of this is what we would call the ball and stick model. This is of the same molecule as to the left of it. The only difference is that instead of writing carbons and instead of writing hydrogens, we are using balls, literally, to represent those. These are color-coded. You'll learn the colors as we go forward, but the white ones are always hydrogens and the black ones are always carbons. So this is just another way that the textbook or a computer program can represent chemical structures. Not writing C's and H's and O's and N's, but giving you orbs or these balls that are different colors, and each color represents a different atom. A lot of times in these model kits, you'll see oxygen being represented as red. You'll see nitrogen being represented as blue. You'll see chlorine being represented as green because it's a green gas. You'll see bromine representing as orange because it's an orangey gas/liquid. And you'll see iodine typically represented as purple. And the reason is because when you heat iodine up, it creates a purple vapor. So these are not randomized colors. These are the traditional colors that we view them as. So why not slap that color onto the sphere in the diagram? However, notice that it still draws the sticks, and these sticks represent a bond. It's important for you to understand, though, that these sticks really are not there. There is no such thing as a bond that looks like that. These things are not sticks that you can literally break or snap in half. That is not how they're structured. It's just a representation that we draw on a sheet of paper to get you to understand that there's some glue that holds these two things together. And that's the easiest and the best way that we can do that. So what you're seeing to the right of it is what we call the space filling model. And this is really how it kind of looks, okay? These sticks are not present. The hydrogens and the carbons are kind of attached to each other in one gobstopper unit. I mean, when I look at that, I think of Willy Wonka and the Chocolate Factory and the gobstopper, because that's exactly what the gobstopper looked like. So it's these hydrogens and carbons that are basically sandwiched all in together. There's no bonds that are present. None of the sticks are drawn, but they are in very close proximity because that glue is still present. They still hang out. They still share those electrons with each other in order to fulfill the octet, and that is why they're hanging out the way that they are. And then finally, to the right of that is the electropotential static map, or the electrostatic potential map for that molecule. So again, we can take this ball and stick model, or we can take the space filling model, or we can take the perspective formula, which is what we call that, and we can sandwich it here in the middle. And then around that structure, we can give you some coloring. And that coloring, again, green is very neutral. So it looks like methane is a very neutral molecule here because it's green almost all the way around. Red areas are negative and positive areas are going to be blue. So this is the structure of methane, but we keep looking at smaller structures. These also stay true to larger structures. So as we get bigger and bigger, this kind of presentation does not go away. So as you see over here on the left, this is the perspective formula of ethane, and you can see the traditional stick bonds. You can see the wedges and the dashed wedges that go in front and in behind. It gives you an idea that this is a tripod to the left and a tripod to the right. So these two things are joined by the two carbons in the center. If you don't like that, computerized models can give you the ball and stick model. Balls and sticks are represented, which is of course why we call it that. To the right of that is the space filling model that gets rid of all of the sticks because in actuality they're not actually there anyway. And then to the right of that is the electrostatic potential map for that particular molecule. And again, we see that this covalent molecule, this organic molecule, is a very neutral molecule. There's no positive, there's no fully negative areas that are associated with it. It is all green all the way around, which means that this thing is neutral, and it also means that this thing is a non-polar molecule, because I don't really see that. Okay? All right, so the next topic that we're going to learn about, now that we're getting more familiar with these shapes, is something that we are going to call a formal charge. So this is the purpose of formal charge. It gives you a shortcut, another shortcut. All right, so the reason here is because if I had a molecule like CH4, and we go through the rules of Lewis dot structure, and we have carbon and we have hydrogen. Carbon has 4, hydrogen has 1. There's a total of 4 of them, so that gives me 8 in total. So those 8 have to be assigned. Which one goes in the center? Carbon. Hydrogens go around it. 1, 2, 3, 4. Everything gets attached to that carbon, and each line took away 2. So 2, 4, 6, 8, and there we go. There's no more. Well, this was a very long, drawn-out process, wasn't it? Right? Who wants to do this every single time that we go through Lewis dot structures? So formal charge is a way that we can predict this structure without maybe going through all of this mess and trying to figure out how many valence electrons, where do the bonds go, and so forth. So here's the story with formal charge. Bear with me because we're going to circle back around and I'm going to show you how this actually relates. Okay? So here we go. Formal charge I'm going to abbreviate as FC. Don't get either one of those grades in this class. There's no sense in it. You can get A's and you can get B's out of here. Trust me, you could do it. Okay, so the FC, or formal charge, and I'm going to do the formal charge for methane, all right? So here is the methane structure, CH4, and what we do, the equation, or the book is going to give you an equation, all right? Do not look at that equation. It's a stupid equation. Don't look at it. It's going to make this process even more confusing than what it is. So here is my advice to you. If you are given a structure first and they're trying to test you and figure out if you know exactly how to calculate formal charge, this is how you'll do it. So they'll want the formal charge on each atom. That is what this is about, which means this hydrogen has a formal charge, This one has a formal charge, this one has a formal charge, and this one has a formal charge. So the way that you calculate formal charge is you find the number of valence that these atoms have. So if you go to the periodic table, you look at hydrogen, it's in group 1A, so therefore this has one valence electron. Well, this hydrogen has one valence, this one's got one valence, this one also has one valence, there's no difference in them, and then the carbon in the center has 4 valence electrons. So that's the first thing that you need to do. The next thing that you need to do is that for every line that is drawn to that atom, that will represent 1 valence. Because keep in mind, the bonds represent 2 electrons, but one of them is coming from one atom, the other one's coming from the other atom, and they're coming together to share those electrons with each other. One brings one to the table, the other one brings the second one to the table. So if they ever split and they get into an argument and they decide to go separate ways, a lot of times that bond will split and one electron could go to one atom and the other one stays with the original atom. Okay? And for every dot that you see on an atom, that also represents 1. So if there's 2 dots, that represents 2. If there's 4 dots, that represents 4. So if you're asked to calculate formal charge, this is how easy it is, folks. Hydrogen has 1 valence. Therefore, 1 is assigned to that bond, and you subtract those from each other. 1 minus 1, 0. There is no formal charge on that hydrogen. It is neutral. This hydrogen to the right, same story. 1 valence. Well, there's 1 from that bond. We subtract those values, and there is no formal charge on that hydrogen either. As you can imagine, the hydrogen down here below, same story. There's 1 valence. With that 1 valence, well, there's 1 from the bond. You subtract those values, and there's nothing there. Over to the left, you see that hydrogen typically has 1 valence. That hydrogen has 1 from the bond. 1 minus 1 is a neutral charge. And then finally, the carbon in the center. Typically, 4A is the group. That means 4 valence. There's 1 from the bond on top, 1 from the bond to the side, 1 to the bond on the bottom, 1 to the from the bond to the left. 4 minus 4 is again 0. All the way around this methane, the formal charge of all of those atoms are zeros all the way across. So you could be asked to calculate the formal charge of each one of those atoms. And folks, this is what we're after. A very stable molecule. A very stable molecule will have atoms that have no formal charge. Charges play a problem in organic. It's a problem in stability. We don't really like it when it happens. So therefore, if you're drawing Lewis dot structures and you begin to assign formal charges to these things that make no sense, they're really high positives or really low negatives, then what this means is that your Lewis dot structure might not be proper. You could have drawn them the wrong way. All right, so let's do another example, and let's kind of cut the fat and go straight to it. So another one of these structures that we did was ammonia, NH3. And this was the structure of ammonia when we did it. Now, the question's going to come around. What's the formal charge for these things? Okay, well, hydrogen has 1 valence. There's 1 from the bond. So that hydrogen has no formal charge. 0. This hydrogen has 1 valence, and there's 1 from that bond. I subtract them. There's nothing there either. This hydrogen has 1 valence. There's 1 from the bond, and there's nothing from there either. And then finally, the nitrogen in the center. The nitrogen, if you look on the periodic table, will be in group 5. It says 5A up at the top. So there's one from that bond, there's one from this bond, there's one from that bond, so there's a total of 3, and then that dot is 4, and then this dot is 5. So guess what, folks? That again is a neutral nitrogen. So there's no formal charge on that compound. Because of that, NH3 is very happy in its structure. Now, what if these 2 dots were not there? And what if we drew another line and slapped another hydrogen on it? And we get NH4 this time. Well, if I look at NH4, there's going to be a problem. All of the hydrogens, they're all the same. 1 valence, and there's 1 from the bond. So this has no charge, that has no charge, this has no charge, and this has no charge. The nitrogen in the center, it normally has 5, and then we subtract 1 for every bond and 1 for every dot. So there's 1 bond, 2 bonds, 3 bonds, 4 bonds. So 5 minus 4 is actually a positive 1. That means the formal charge on that nitrogen is a positive, which means that this molecule is no longer neutral, which means that the nitrogen in this area of the molecule will be a positive red area if we are to represent that with computer mapping or electrostatic potential mapping. It also means that this is a squiggly positive or a full-blown positive in that area, and that also means that that positive will go out and look for negatives to bond up with in order to satisfy that charge. This is an unstable molecule the way that it is. It's going to want to neutralize itself out, and the problem area is that nitrogen in the center because it has a formal charge of a positive 1. Okay? Another structure that we did was water. Here was the structure of water. We accepted this as the fact of water right there. So I can do the same thing. Hydrogen has 1 valence, 1 from the bond. There's a neutral charge. Here we have a neutral charge. Oxygen's in group 6A, so there's 6 valence. So I'm going to subtract 1 for every bond and 1 for every dot. So there's 1 bond, 2 bonds, and then there's a 3 for that dot, 4 for that dot, 5 for that dot, and 6 for that dot. So 6 minus 6 is 0. So this oxygen has a neutral charge as well. That means that this molecule, formal charge-wise, is very happy. None of these atoms are put into a position where they are uncomfortable. And when they become uncomfortable, they become reactive. And they will want to change. They will want to do things later down the road. And we don't really want to see that sometimes. So this is a very good representation that that Lewis dot structure is very acceptable to all of the atoms that are involved in that structure. Okay, now what if we had a water molecule with an extra hydrogen on it and it looks something like this? Is that acceptable? Well, this would be H3O. Okay, and we've seen that before. That's in general chemistry, that H3O is basically a representation of H+, which is also a representation of acid. This is a way that we represent acid in chemistry. So is this molecule acceptable? Well, it is temporarily. It is for now. But the reason that it's not long term, this hydrogen has no formal charge. That one has no formal charge. This one has no formal charge. That oxygen in the center, 6 valence. There's 1, 2, 3 from the bond, and then there's a 4th and a 5th from those dots. So 6 minus 5 is actually a positive 1. So this oxygen carries with it a positive charge. Well, folks, that's not surprising because look at what we did down here. We wrote H3O+, and then to shorthand that, we wrote H+. We knew that that positive was there. This was not surprising to us, but this is how we determine those charges. It's one of the reasons that those charges are going to be present. So due to the formal charge, we can calculate that oxygen is problematic here. That positive charge for oxygen is a +1. It doesn't like that. It wants to be neutral and get to that formal charge of 0 whenever it can. So if it can find a way to fix that problem, it's going to do it. And this is one of the ideas of formal charge. Now, I told you that formal charge is going to be a shortcut for Lewis dot symbols, and this is why. For hydrogen, you really only want one bond that's going to be present. At that point is when hydrogen carries a formal charge of 0. So every time that I'm drawing hydrogens in organic chemistry, I typically only want one bond that will go to it. And the reason is because formal charge. Also, octets involved, but formal charge can be used as an argument as well. As far as carbon goes, the shortcut here is you're going to have 4 bonds every time. Carbon has 4 valence. 1 from each bond will give you a total of 4. 4 minus 4 is 0. Okay? Every time we draw carbon in organic, it will have 4 bonds, as bad as it can get 4 bonds. If there is a way that it doesn't have 4 bonds, maybe 3, it will try to find measures to get that 4th bond whenever possible. Oxygens. Oxygens are very happy with 2 bonds, and oxygens will then need 2 sets of electrons. 2 sets of electrons here, giving you a total of 4. All right, so 2 bonds, and there's my first set, and there's my second set. Again, it's a shortcut now. We know every time we see O drawn in a structure, O will have 2 bonds to it and 2 sets of electrons if this is the normal, happy oxygen that we have in our structure. Up here, I can draw carbon with 4 lines. Here, I'll draw hydrogen with 1 line. Any of our halogens, and halogens I represent with a X, and halogens represent your fluorine, your chlorine, your bromine, and iodine. That is a name to a family that you should have learned in general chemistry. All of that column has a common group name or family name, and that is a halogen group. In organic, we do represent that with an X because we can talk about any of those halogens as they're very common. So X represents halogen, which represents either fluorine, chlorine, bromine, or iodine, maybe all of the above, maybe just one. The way that they work is that you are going to have 1 bond that goes to them, because keep in mind they have 7 valence. So there's 1, there's 2, 3, 4, 5, 6, and 7. So anytime I see fluorine, chlorine, bromine, or iodine listed, anytime I see them, I'm going to assume that I only draw 1 bond to them. That's it, no more. And then I put enough dots around that halogen in order to have a total of 6. This is where I get my formal charge of 0. There's now 7 present, and those 7 will cancel out, and I have a formal charge of 0, which makes the halogen very happy. Nitrogen is also a common one. Nitrogen has 5 valence, all right? So the way that these things work is that they typically will have 3 bonds, and then they will have 2 electrons associated with them. So there's 1, there's 2, there's 3, there's 4, and then there's 5. So again, a shortcut. If I'm asked to draw a Lewis dot structure and it involves nitrogen, this is where my mind goes every single time in the beginning. I know that nitrogen has to have 3 bonds, and those 3 bonds will also come with 2 electrons, and that is the typical setup of nitrogen every single time, meaning that I would never have a scenario where nitrogen has 4 bonds, because now this formal charge is not 0, and it doesn't like it. This also means that I would never have a fluorine in a structure that has 2 bonds that are attached to it. That does not make it happy with formal charge. So this is not acceptable to that atom and to that molecule. As far as the oxygen goes, I would never have 3 bonds on one side and call it a day. Or I would never have 3 bonds on one side and a bond on the left. It needs 2 bonds. with 2 sets of electrons. If you are drawing this in the Lewis dot structure, this is incorrect. You know it's wrong right off the bat, because that is not how these oxygens want to be. As far as carbon goes, you would never have 2 on one side, 1 here and 1 there, because that is a total of 5. It only needs 4 bonds. That's it, no more. So if you're finding yourself drawing Lewis dot structures and you're seeing 5 bonds that go to this carbon, there is something wrong with your structure. You are doing it incorrectly. So you got to go back to the drawing board, try to figure out another scenario, because it's not going to happen, folks. And that's also the same reason of hydrogens. You would never see 2 bonds that are drawn to hydrogen because it can't handle them. To get that formal charge of 0, it only needs 1 bond, and that is it. So this is the story with formal charge. Again, they are going to give you a crappy equation in the textbook that looks something like this down here below. Number of valence electrons minus lone pairs plus 1/2 of the bonding electrons. I mean, it makes no sense at all. So my advice to you is to ignore that equation in the text. They actually word it a very strange and confusing way. So just keep in mind, 1 for every bond, 1 for every dot. That's all that you need. So you take the valence electrons minus 1 for each bond or line, and then minus 1 for each electron dot. That's all that you have to have. All right, so here we get an example, and it says, what's the formal charge of? And it says oxygen atom in water, or the oxygen atom in hydronium. We've actually already done this, okay? The oxygen atom in hydroxide. Well, I can do this one really quick. Hydroxide is OH. There we go, okay? Oxygen's got 6 valence. Hydrogen has 1 valence. This gives me a total of 7. There's 2, 3, 4, 5, 6, and 7. Okay, so maybe that's the way that I need to draw it. This formal charge for hydrogen, 0. There's nothing there. 1 valence minus 1 from the bond. That's pretty good. It's pretty happy. This oxygen, though, here in the center normally has 6 valence from the periodic table. Well, we take 1 away from the bond, so there's 1. And then 1 for each dot. 2, 3, 4, 5, 6. Does that make sense? Well, no, because look, you have this minus 1. So we need to go back, and we forgot to add that 1 up there, right? That's an ion. We need a total of 8. So therefore, there's the matching pair. Pairs of electrons is what we normally see. And now we take 6 minus 1, 2, 3, 4, 5, 6, 7. So 6 minus 7 is a negative 1. So that oxygen has a formal charge of a negative 1. The nitrogen in ammonia, we did that too, and the nitrogen in the ammonium ion, which is that NH4+. We've already done that one as well. So there's you an example of formal charge, a couple of examples actually that I just wrapped in all together, and we talked about it at once. Here's another example of formal charge. So this is the formal charge of carbon dioxide. This is another shortcut method that people tend to do. I don't really talk about it a lot because I think mentally you do this anyway. But if we were to assign the formal charge on this particular carbon, 1 from each bond, carbon normally has 4 valence, so 4 minus 4 is 0. Oxygen typically has 6 valence, so 1, 2 from the bonds, and then 3, 4, 5, 6 from the dots. So this actually has a formal charge of 0, and that one has a formal charge of 0 as well. So once again, just another way or another representation of how to do these formal charges. So folks, this could be a lifesaver for you, especially later on down the road, because if you can remember these rules that you're seeing on the screen right now, then your job of drawing structures and making sure that they make sense and organic will be much, much easier at the end of the day. Okay, so that's where we're going to stop this video. In the next video, well, there are ways that we can get formal charges, and they do stick around a little bit, and they have time to do things for us. So we're going to have to put a name to some of these. And because we're talking about organic, we're talking about carbon-based molecules, we're going to focus on carbon first. So carbon can have a formal charge. So we're going to talk about those, we're going to provide them names, and you're going to see especially one of them over and over and over throughout the semester. So stay tuned, come back, don't take any breaks. I know that you're on a roll. I know that your hand might be cramping a little bit right now from writing down all of these notes, but it's going to be worth it in the end. Just think about that. So I'll see you when you come back.